Hello, everyone, and welcome back. In today's episode, we will be doing day one of three on volumes of three-dimensional objects and how volumes of three-dimensional objects can be calculated using integrals. Now, to a certain extent, this is an idea that we've already seen appear several times throughout this course, even as early as Season 1, Episode 2, when we used a sum, when we used a left Riemann sum, for example, to estimate the volume of a three-dimensional object from data collected about its cross-sectional areas. If we had an object and we sliced that object at different positions and we measured the area of that slice, then the volume could be found by taking the area of each slice and multiplying it by the delta x, the difference, the distance between the measurements. And if we take that same idea and we take a ton of measurements with very little space between them, allowing delta x to approach zero, then that Riemann sum estimate for the volume becomes a perfect integral calculation of the volume. We have seen that the volume of the object can be found by simply integrating from the lowest x value to the highest x value the area function dx. So the only thing that we will be doing in the next 3 days that is different from what we've done before is that we are going to have to work a lot harder to find the area function a of x in our problems. The challenge of these problems will be to find the function that will tell us the cross-sectional area at any particular x value. And once we have found that function, we can get the volume simply by integrating. Now, to give you an example of one such challenge, let's consider the following scenario. In this scenario, I'm dealing with a three-dimensional object, and I'm given these two sort of hints about the object's shape. Hint number one, if you take the object and you set it down on a surface, a flat surface that can be represented by the xy plane, then the base of the object, the footprint of that object, occupies a certain region on that surface. And the region occupied by that object on that surface would be shaped like a right triangle, with one vertex at 0, 0, another vertex at 1, 0, and another vertex at 1, 1. So that's our hint about what the bottom of the object looks like. The second hint about the shape of this object is that if we took a knife and we held that knife parallel to the y-axis, and we sliced the object, then the shape of the slice that we make would be a semicircle. Now, let's see if we can find the volume of the object being described in this sort of riddle. To find the volume, all we have to do is find a function that will tell us the area of each of these slices that we are told are shaped like semicircles. If we can find the formula for the area of each slice, then all we have to do is integrate the area function, and that will be enough to find the volume of the object. Now, in a situation like this one, where the information given to me about the object is so complicated, the very first thing that I try and do is I try to draw the object in question. I'm not a very good artist. I haven't really trained, but even so, a sketch, even if it's messy, can help me to wrap my mind around what this question is telling me. The first thing that I will do is I will try to draw this object by hand, because that is what you would have to do, right? If you were going to draw, you would have to draw the object by hand. But then for clarity, I will also show you what this object looks like using a computerized drawing that will be a little bit more clear. So exercise number 1, attempt to draw the object described in these bullet points. Try to draw at least the base of the object on the xy plane, as well as at least one of the slices that's being described here. So I'm going to start with a pair of axes, and I'm going to go ahead And for clarity's sake, I'm going to draw the x-axis and the y-axis in different colors. So here is the x-axis, which I'll draw in red here, and then I'll go ahead and draw the y-axis in green. And if you cannot see the difference between red and green, I also will label these axes. X is horizontal and Y is vertical, as is tradition. Now, on this two-dimensional picture, I'm going to go ahead and draw the object's base. And to draw the base of the object when it is sitting on a table, I'm going to use the info in this first data point. If I set the object down on the XY plane, the base of the object would occupy this region, a right triangle with vertices 0, 0, 1, 0, and 1, 1. So I'll go ahead in pink, I suppose, and I will draw in a triangle with vertices at 0, 0, 1, 1, and 1, 0. So this triangle here in pink, if I set the object down on a table, the image of that object on the table would be this triangle. So now I'm going to draw the same picture, but I'm going to try and draw it in perspective in three-dimensional space. So I will go ahead and let the x-axis be angled toward me, and I will let the y-axis go off to the side. And then the various heights of the object would be going up and down in this picture. And so if I were to recreate this triangle drawing over here on the left in this image, then I would be going from 0, 0, where x and y cross, up to a location that's 1 unit along the x-axis, up to a location that's at 1 and 1 along the x and the y-axis. So in perspective, that would be this table, this portion of the table right around here, roughly speaking. Okay, so now I've drawn the base of the object both on two-dimensional space and within three-dimensional space in perspective. So I have now made sense of the information in this first bullet point. Next, let me try and make sense of the information in this second bullet point, where they say if we took a knife, held it parallel to the y-axis, and sliced the object, the shape of the slice that's formed would be a semicircle. So in two-dimensional space, the kind of slices that we're taking are parallel to the y-axis. So I might go in, pick a random x value, say here, and I might go ahead and slice the object along this white line. In this three-dimensional picture, that same slice would show up like this, parallel to the y-axis. They say if you slice the object in this way, then the slice that you get is shaped like a semicircle. So I'm going to draw in a semicircle above that cut. And this guy in white would be the shape of a random slice taken at a random x value. So now that I've tried to make sense of this image in a handmade drawing, let me show you what this same image looks like in a 3D drawing on the computer. And to that end, I'm going to go ahead and use GeoGebra 3D. It's a pretty fussy program, so I don't expect you to actually learn how to use it, but I personally would like to use it to show you what's going on in this situation. So here in red is our x-axis, here in green is our y-axis. X is coming toward us, y is off to the side. And here in blue is the right triangle, the same right triangle that we drew in our picture in pink. Now, what is going on with this purple sector here? I give the program a random x value between x equals 0 and x equals 1, and it is cutting into the object, and what we are seeing in purple is the semicircle shaped slice that is being cut into the object at that point. So if I let that animation run, you can see the various slices of the object, the various cross sections of the object at different positions there. So perhaps an image of the object is being formed in your mind. In my opinion, this object feels a little bit like a cone, right? Like a cone that's been cut in half and then placed down on the table along the cut that was made. This looks like an object that's shaped kind of like a cone. So that's exercise one. Simply try and make sense of what you are being told in the question, and a drawing can be helpful with that. Step number two, let's see if we can find this function a of x, which will be able to tell me the area of a cross section taken at a random x value. These cross sections, we're told, are all shaped like semicircles. So if I want to find the area function for these slices, then I'm probably going to be using the formula for the area of a semicircle, which is 1/2 times pi times the radius squared. So let me go ahead and see if I can figure out what would be the radius of any particular slice. If I can find the radius of a random slice, then I can put that information into this formula to get the area of a random slice. Scrolling back up to my picture, if I took a random slice at a random x value, then the slice I would get would look like this one here in white. Now, question. Based on the information given in this problem, based on the information given in this picture, can you tell me how long is that slice that we just cut? Well, I'm noticing that on this entire diagonal line here in pink, this pink line is connecting 0, 0, and 1, 1. So in this particular problem, every point on this diagonal line has a y coordinate and an x coordinate that are the same. The x coordinate is the same as the height. Because of that, if this cut is taken at an x coordinate randomly called x, the height of that slice, the width of that slice, will also be equal to x. Because the y's and the x's are equal, and the width of that slice is the same thing as the height of that point on the triangle. Now let's think about what that bottom slice is doing and how that bottom slice shows up in the semicircle whose area I'm trying to find. In the semicircle, that slice shows up as the diameter of the circle. The slice that I made forms the line segment that cuts directly through the middle of the circle. The slice that I made forms the line that cuts directly through the middle of the circle. In other words, the slice that I made forms the diameter of this semicircle. So if the diameter of the semicircle is x, the radius of the semicircle must be 1/2 of that x. Half of the diameter is what gives you the radius of a circle. So having observed that, all I need to do is go into this problem and plug in 1/2 x for the radius of the semicircle taken at a random x value. And if I plug that in, then my a of x formula becomes 1/2 pi times the quantity 1/2 x squared. And if I simplify that, I get 1/8 times pi times x squared from this half times these two halves. This is my area function. If I give you any random x value, then you can plug it into here and you will know exactly what is the area of the corresponding slice taken at that x value. Okay, so now that I have established the area formula, if I want to find the volume of this object, if I want to calculate the volume of the object, then all I have to do is integrate this area formula with respect to x. And at this point, we have so many tools and tricks that this one is not so bad. The volume of this object is the integral from the smallest x value to the largest x value, 0 and 1 in our case, of the area function, which is 1/8 pi x squared dx. Just copy pasting what we had here. And the antiderivative of that would be 1 over 24 pi x cubed, evaluated at 0 and at 1. And so the volume would be precisely pi over 25 cubed units. This is how we can find the volume of a three-dimensional object given information about its slices. If we have information about its slices, then we try to use that information to find an area function for those slices, and then all we have to do is integrate that area function, and that will give us the volume. Let's do one more example just for the variety. In this situation, someone says, okay, I got an object, and if I set it down on the xy plane, the base of the object occupies the following region. It's the region that is bounded between the following three curves: this exponential curve, this linear curve, and this straight vertical line, x equals 1. So this is describing the object's base. Here we have some information about the slices. If I sliced the object parallel to the y-axis, then the shape formed by those slices would be, in this case, squares. So let's see if we can calculate the object's volume from this information. Now, as before, the very first thing that I am going to do personally is I'm going to use a couple of drawings to help me to get some purchase on this problem and understand what is going on. And I'm going to start, as before, by separately drawing the base of the object in two-dimensional space. Here's the x-axis, and here comes the y-axis. This is where I will draw the object's base. And then I will attempt to recreate that drawing in three-dimensional space with x toward me and y to the side. And then I will recreate the base in this three-dimensional picture and try and draw at least one cross-section. Okay, so as far as the base is concerned, the base is kind of complicated this time. They're saying to me that the base of the object occupies the region bounded by these three curves here: exponential, linear, and linear. Now, if I go to Desmos, the region in question is the one right here, bounded by exponential in red, coming up curved shape, x equals 1 here in green, and y equals minus x here in blue. So let me recreate this drawing and the region in question in my personal picture here. Okay, so here comes the swoopy part of the exponential. Y equals e to the 2x. Below that is the line y equals negative x. I'll make that blue. And then we stop at a value of x equals 1 on the right side. Okay, and the region we care about is the one that is in between these three curves here. Now let me try and recreate that picture in three-dimensional space. So here is the curve coming out in the positive y and x directions. Here is the line coming down in the positive x and negative y direction. And here is the x value where we will stop. The x value where we will stop is x equals 1. It's this guy right here. And so if I take a slice out of this object at a random x value, slice taken, for example, right here, I'll mark it in gold, x, then that slice will show up on the picture here. And what they're saying is sitting above that location is a square. So here we go, shaded in yellow is one of these cross sections. In yellow, I have the square cross section that I get from cutting this object. So once again, my mission is to find my area formula. And once again, because my areas have a geometric shape, and in this case, they have the shape of squares, I'm going to use the area formula for a square, side length squared. Side length squared, if I can just figure out what is the side length of an arbitrary slice taken at an arbitrary x, then I can put that side length into this and I can finish filling out my area formula. Now what I can see in the picture is that the side length of this square is going to be exactly equal to the length of the cut which I made in this picture, right? At an arbitrary x value. So what I really need to figure out is if I cut at an arbitrary x value in this picture, what is the width of this slice that I have made? And to answer that question, I'm going to observe that these slices stretch between y equals e to the 2x at the top and y equals negative x at the bottom. So what is the distance between those quantities? The distance can be found just by subtracting those quantities. Take e to the 2x and minus negative x, and the length of that slice, the side length of my square, is going to be the difference between them, e to the 2x plus x in total. Now let's go ahead and plug that information in here to get my area formula. The area formula is just the squared side length. So plugging in the side length formula that we found from our picture, this simplifies to e to the 4x plus x e to the 2x plus x squared. And to finish this calculation, all I would have to do is integrate my area function from the smallest x value in my problem to the largest x value in my problem, which I was told once again, the largest x value should be x equals 1. Now to do this calculation, I will start by using sum rule to separate this into e to the 4x, x e to the 2x, and x squared. I can integrate this first expression using chain rule. Let me break it down into parts. Or, more appropriately, since we're doing integrals instead of derivatives, I should say substitution. This integral in the back is really straightforward. This guy could be found just using power rule. And what integral technique do you think we will be applying to this guy in the middle, where I have the product of x and e to the 2x? Well, this is a situation where I think I cannot use substitution to help me with this product, but I think perhaps integration by parts will work here. So let me try that on this middle integral. So one step at a time, if I were to integrate from 0 to 1 e to the 4x dx, then I would let u be equal to 4x, so that du was equal to 4 dx, so that 1/4 du was equal to dx. If I substitute that information into this integral, then I am integrating e to the u du times 1/4. The antiderivative of that is e to the u, once again, plus c, and then I will replace u with what it truly is equal to, 4x plus c. That's the integral of e to the 4x. And to translate from this indefinite integral back to this definite integral, all I'm going to do is drop the plus c and then plug these two limits of integration into my antiderivative. This would be the value of integral number 1 in this sum. For integral number 2, I think I'm going to have to use integration by parts to make this manageable. So I'm going to let u be equal to x because that becomes much simpler when you take its derivative. I'm going to let v prime be equal to e to the 2x because that becomes not so bad when you take its antiderivative. And using chain rule once again, really, the antiderivative of e to the 2x can be found pretty simply. If the antiderivative of e to the 4x is 1/4 that same exponential, the antiderivative of e to the 2x is just going to be 1/2 exponential. Now, if I put this information together into my integration by parts formula, it says that the integral of x times e to the 2x is equal to 1/2 x e to the 2x minus the integral of 1 times 1/2 e to the 2x dx. And once again, if you're integrating e to the 2x, then substitution causes another copy of 1/2 to pop out, giving me in total 1/4 there in the back. This is the indefinite integral, and if I wanted the definite integral, all I would have to do is plug x equals 1 and x equals 0 into this result. And so from part 2 of this integral, I would get 1/2 times 1 times e to the 2 times 1 minus 1/4 e to the 2 times 1. And then taking away the same quantity, but with 0 plugged in for x, 1/2 times 0 times exponential vanishes, and then 1/4 times e to the power 0 is 1/4 times 1. So after simplification, I get 1/4 e squared plus 1/4, and this is the value of this second integral in my area. The last integral is the easiest one to actually calculate. Integral from 0 to 1 x squared is just 1/3 x cubed evaluated from 0 to 1. So that's 1/3. And so the total is our volume, the result of the first part of the integral, which is 1/4 e to the 4th minus 4, 1/4. And then this second part of the integral, which is 1/4 e squared plus 1/4. And then this final part of the integral, 1/3. These three quantities together would give me the exact total volume of the object described in this problem. And we can clean this up a little bit if we want to.